All right, so we left off yesterday, sorry, Monday, having just described the various ways we might specify the equation of a line in R2. And I just wanted to say a couple words about the different uses of these different formats. Okay, so let's note that, for example, the vector equation of a line great for producing points on a any value of t. Is y on the line, right? This is because, remember, the vector equation of a line is given as follows. X naught, y naught at some point we know is on the line, plus t times some parallel vector, right? So every value of t, first of all, these are known, right? X naught, y naught, and a comma b. These are known quantities. So every value of t that you pick, you produce some point on your given line. Okay. So you're looking to find a point, an arbitrary point on a line. The vector equation is very useful. You pick a value of t. Now, by contrast, the standard and the metric equations are great for determining if a particular point lies on a given line. Right? That is to say, given a vector, or sorry, given a point x comma y, if I want to determine if this lies on a line I know the standard or symmetric equation of, I just plug in those values of x and y and see if I get a true statement, right? If I get a false statement, then the point does not lie on the line. If I get a true statement, then it does in fact lie on the line. Okay, so these are really the main takeaways from all these different forms of equations of a line that we went through on Monday. Now, we'll talk more about this when we talk about lines in R3, which we'll get to later today. The symmetric equation has an additional useful application in R3. We'll talk about that after we talk about a somehow more natural generalization to 3 dimensions, planes in R3. How come I didn't take the time to talk about planes in R2? Yeah. There's only one plane in R2, the whole plane, right? You're on a plane. You can't specify any plane other than the whole plane itself. When we move up a dimension, planes become the analog of lines, right? That is to say, here's the pattern. When we're in R2, we talk about lines because they're the thing that's 1 dimension less than the entire space. When we're in R3, first we'll be concerned with planes, the thing that are 1 dimension less than space. Right? And then we'll go a little deeper and talk about lines as well. But the natural thing, the natural linear thing for Rn are the objects of dimension n minus 1. Okay. All right. So analogously, in R3, we may specify a plane by a single point on the plane x naught, y naught, z naught. And a vector normal to the plane. And hat A, comma B, comma C. Okay, so I know what I was just saying is kind of vague, the natural thing to consider. What I mean is we can imitate the construction of a line using a point on the line and a normal vector in R3, and what we get is a plane. Right? When we imitate the construction, what we get is something that's one dimension less than the entire space. Okay. So here's the theorem. Given a vector A, comma B, comma C, which is not equal to the 0 vector, and a point x naught, y naught, e naught. The unique plane containing our point and having n as a normal is given as the set of points x, y, z satisfying A times x minus x naught plus B times y minus y naught plus C times Z minus Z naught is equal to 0. Or if you like, again, something that will become second nature to you in no time at all, I promise. You can factor this as a dot product. Again, reiterating the fact that this vector n is normal to the plane that we're specifying. Now, it's completely analogous to the definition we gave for a line, right? We just have an extra component. Okay. So let's completely reproduce what we did in R2. If we let D be equal to negative A x naught minus B y naught minus C E naught, we get the standard equation of a plane in R3. AX plus BY plus CZ plus B is equal to 0. Okay, so let's do a little practice with interpreting such things. So consider the plane P given by the equation 6x minus 5y plus 3z minus 7 equals 0. Let me ask you to find a normal vector and determine a point on the plane. Okay, so I just give you an equation in standard form. How do I find the normal vector? Yeah. Yeah, it's the coefficient on the variable, right? Remember when we talked about the standard equation of a line, determining a normal vector, the constant term doesn't matter. That just specifies where the line is. It doesn't change the slope of the line, right? Changing this, analogously, changing this constant term, you get the same tilt of the plane, but changing this constant term gives you parallel copies of it, right? So that is to say, you can always get a normal vector from the standard equation of a plane just by looking at the coefficients of x, y, and z. Coefficients of the variables give you a normal. That is to say, we could take n to be 6, negative 5, 5, negative 5, 3. Why do I keep saying find a normal? It gives you a normal. What is the meaning behind this indefinite article? How come I'm not saying the normal? Yeah. Yeah. What's another normal vector? Yeah, good. So you just multiply this by -1, right? Another normal is negative n hat or -6, 5, 3. Oh, sorry, -3. Okay, here's a visual representation. Here's my plane. Here's a normal. I can scale this by any factor, and it's still going to be perpendicular to the plane, right? This is the scaling that we're talking about now. I flip it. So I say a normal because there's infinitely many normals. How does that manifest in this equation? Well, what that means is that if I multiply this equation by a constant all the way through, it still specifies the same plane, right? Okay, so let that sink in. That's in part because I'm still equal to 0, right? That's just changing the magnitude of my normal vector that I get from the coefficients. The vector still points in the same direction. Okay, and all the same points, x, y, and z, will still satisfy this, even if I multiply it by a constant. Right? Okay. Now, how about the second part of this question I asked? How can I determine a point that lies on the plane given by this equation? is a very non-specific question. Yeah. Okay. Now, in the theorem, I gave you some formula for what the constant term means in terms of the point that lies on the plane. Is that helpful here? Not really, because there's lots of ways I can find multiples of 6, -5, and 3 that add up to 7. But that doesn't really help me in actually finding them. Since I'm not asking for any particular point, I'm going to make this as easy as possible for myself. What I'm going to do is just choose two values for x and y and determine what z must be. Okay, and again, I want to reiterate this. Very often, mathematics is about doing the least work possible. So if I want to do the least work possible, what should I choose for x and y? Yeah, I can take 0 for both of them, right? So to find a point, let x equal to 0, y, and solve for z. So what do we get? 6 times 0 minus 5 times 0 plus 3z minus 7 equals 0. I do some arithmetic, and I get z is equal to 7/3. So point 0, 0, 7/3 lies on the plane. Not so bad, right? Okay. So now, at this point, when we were in R2, we considered, instead of a normal vector, how we could specify a line by a parallel vector and a point vector the line goes through. So let's suppose now we would like to parameterize a plane in R3, like we did for lines in R2. Well, here's the problem. When we discussed lines, we only had to specify a single parallel vector, right? Here I have a plane. Well, let me orient it this way. I have a plane here. Let me take some parallel vector. All of these different planes, as I move this around, these are all distinct planes, right? And they're all parallel to this vector. A single parallel vector is not enough to specify a plane. Okay? We actually need a pair of parallel vectors, which are not parallel to one another. A single parallel vector is not enough to parameterize a plane. So here's what we have to do. Here's our analogous theorem. Given two non-zero, non-parallel, vectors, let's say A hat and B hat, and a point. X naught, Y naught, Z naught. Then there is a unique plane. Containing our given point and parallel to both A and B. A arbitrary point X, Y, Z is on this plane if and only if there exists scalars U and V, so that our arbitrary point is equal to, what am I going to write here? Anybody tell me? Fill in the blank. What this equals? I have two parameters now. Think back to what it took to write the equation of a line parallel to a single vector. We scaled that vector. What should we do here? Yeah, we'll use U and V as the scalars for A hat and B hat. And so we take the point that we know is on the plane plus U times A hat plus V times B hat. Okay, so again, this is what we want, the uniqueness of this plane. Right? If I take a single vector in R3, I can find many planes which are parallel to that vector that contain a given point. But once I specify two vectors and a point that must be contained in the plane, I get uniqueness. This is the important feature that we would like to pay attention. Okay. Okay. So let's do an example. Okay, so again, let's let P be given by the same as before, right? This standard equation. Let me ask you to find a standard equation of form 3x plus by plus cz plus d is equal to 0 for the plane Q, which contains a point 2, 1, 3, and is parallel to the plane capital P. Okay, so I'm giving you a lot of information here, but I'm ultimately just trying to find the coefficients B, C, and the constant term D, such that I necessarily contain this given point, and I want to simultaneously be parallel to the plane P. So let me give you a word of advice here. Let's try to ensure that P is parallel to Q first. And then after that, we'll check to see how we can make the point 2, 1, 3 necessarily lie on Q. So how should we go about ensuring that Q is parallel to P? Yeah. Yeah, right. So another way of saying that's exactly right. But how we use that fact is to say that the normal vector for this plane, a normal vector for this plane, must be parallel to the normal vector for this plane. That's exactly what you said, just rephrased slightly, right? Okay, good. So how can we ensure that the normal vectors for P and Q are parallel? What do you mean by same? Yeah, exactly. One's a scalar multiple of the other, right? Okay. So to ensure parallelness, make normal vectors parallel. That is to say, we want this normal vector n sub p, right? I'll just work the normal of p to the vector 6, -5, 3. Is equal to t times the normal vector for this plane Q. So I've given you that the first component is fixed at 3, and I'm looking to find B and C. Okay. So turns out that's enough to determine what the scalar T is, right? Yeah, I guess I should call this the normal of Q. Okay, so since we must have 6 equals 3t, this implies that t is 2. Yeah. Okay. So we get equation -5 must be equal to 2 times b, and 3 is equal to 2 times c. Right? Or in other words, B is equal to negative 2/5, and C is equal to 3/2. Oh yeah, I'm sorry, 5/2. I've actually been pretty good so far, but I'm very error prone when making computations. So watch me. Sure, I don't make mistakes. Thank you. Good. So this determines B and C. What we have yet to do is determine D. How can we determine D? Yeah. Exactly. Great. And luckily, we were asked to ensure that this value lie on the plane. So we should just plug that in to determine what D is. Good. Find D. Plug in 2, 1, 3. So we get 3 times 2 plus, oops, sorry, B is negative. Yeah, minus 5/2 times 1 plus 3/2 times 3 plus B is equal to 0. And in an effort to make fewer mistakes on the board, I computed this beforehand. So do the arithmetic, verify that this is true. But altogether, this gives you that D is -8. So the plane Q is altogether given by 3x minus 5/2 y plus 3/2 d minus 8 is equal to 0. Okay. So that's pretty much all. Yeah, right. So yeah, remember I was just trying to come up with an equation of this form. So once we come up with the constant K, C, and G, we're done. Okay, so that's pretty much all I wanted to say about planes in R3. Familiarize yourself with this short amount of material. It's going to be very important to us in the next month. Okay. But now let's talk about lines in R3. Okay, so let me say this. Writing the parametric equation a line in R3 is just the same as in R2. What do I mean by that? Well, let me tell you what I mean by that in the form of a theorem. And then I'll ask you to look back at your notes for how we describe the parametric equation of a line in R2 and compare it with what we say here. So let's let V be a vector ABC, which is not the 0 vector. And x naught, y naught, z naught, a point. Then an arbitrary point, x, y, z, is on the line parallel to V containing x naught, y naught, z naught. If and only if there is a scalar t so that x, y, z is equal to our point x naught, y naught, z naught, which we are given, plus d times b. Okay. So here's the thing. When we were talking about planes a minute ago, and we wanted to parameterize a plane in R3, we had to give two parameters, right? That corresponds to the dimension of the object we're describing. Here, even though we're in R3, we only need one parameter to describe this one-dimensional object, a line, in R3. Okay. So, over the times that I taught this course, I perhaps emphasized that fact less in the beginning. But in general, this is the case. If you want to parameterize something n-dimensional, you need n parameters. Okay? Remember that. Okay, so this, of course, can be expanded, just like we expanded the case in R2. Right? This is the same as x naught, y naught, z naught, plus dA, dB, c, or if we like, we can combine this into a single vector, each of the components of which are an equation for a line that we're familiar with. Okay, so again, these are the components here are the parametric equations. This is just a piece of terminology, like before. The vector equation of a line and the parametric equations are the components of the vector equation. Same scenario here. Okay. So just as in R2, we can take the parametric equations of a line and simultaneously solve for t for each of them, right? So simultaneously solving the parametric equations for t, we arrive at the symmetric equation. Right? And this also should look somewhat familiar. What have I not said here that is necessary to make this calculation? That is to say, what is the only way that this makes sense? Yeah. That's true, yeah. So t is equal to each of these three quantities, but why am I allowed to form this? Yeah.
Is it not the zero vector on one?
Yeah, all three of A, B, and C must be not equal to 0 in order for me to write this, right? I can't divide by 0. Good, thank you. where all three of A, B, and C are non-zero. So here's the thing. This name is somewhat misleading, right? Because it's actually two equations, right? We have two equalities. We still call it a symmetric equation, but it's actually two equations. So note there are two important equations here. We have this equation, and we have this equation. So here's the geometric interpretation of what's going on here. X minus x naught divided by a equals y minus y naught divided by b is the same as saying b times x minus x naught minus a times y minus y naught equals 0. What is this an equation of? Yeah, it is a dot product. What geometrically does this specify in R3? Anybody? We're just talking about these things. This specifies a plane. Right? It's the standard equation of a plane where c is equal to 0. The coefficient on c minus c naught. So I'll write this out, where this is actually v times x minus x naught minus a times y minus y naught plus 0 times v minus v naught equals 0. A plane. Similarly, let's take the other equation that's implicit in the symmetric equation. And also, y minus y naught divided by b equals z minus z naught divided by c implies or is the same as 0 times x minus x naught plus c times y minus y naught minus b times z minus z naught equals 0. Also a plane. So the symmetric equation is actually the equation of two planes in disguise. And because we're setting all three of these quantities to be equal, the line that we're specifying by a symmetric equation is where this plane and this plane intersect. Okay? That's the consequence of having all three of these be equal. We want the points that satisfy the symmetric equation to lie on both this plane and this plane. So we have two planes that intersect in a line. That's what the symmetric equation gives you. Okay, so what happens when one or more of A, B, or C is 0? So it doesn't look as nice here, but the geometric intuition is the same. The pair of symmetric equations is two equations of two planes that intersect in a line. Okay, for example, if, what did I write down for an example? If C is equal to 0, then the symmetric equation has form x minus x naught divided by a equals y minus y naught divided by b. That's one equation of a plane. And we just let z equal z naught. Okay. Look back at the parametric equation. If c is equal to 0, I just have z being a constant, z naught, it doesn't change. So that's reflected here. Okay, so in 3 dimensions, when you specify one of x, y, or z to be a constant, that gives you a plane, right? Z equal to z naught is the plane that's parallel to the xy plane at height z naught. Okay, and where that plane intersects with the plane given by this equation is the line that's specified by this symmetric equation. Okay. All right. Doing great. Do an example. Okay. So let's let P be plane given by 3x plus 2y minus z plus 6 equal to 0. And L line through the points 5, 3, 0 and 6, 2, 2. What I'll ask you is to determine the points of intersection of P and L, if any. Okay, so what are the possibilities before we start trying to compute anything? What can happen here? Yeah. The line of the plane could be parallel, which tells us what about their intersection? Exactly. Very good. So here's my line. Here's a vector that's in my line. If I'm parallel to the plane, I'm either not touching the plane ever, or I'm actually on the plane, in which case the intersection is the entire line. Or I could have no intersection. Or I could have exactly one point of intersection if I'm non-parallel to the plane. Right? Those are the 3 possibilities. One point of intersection, no points of intersection, or infinitely many, all points on the line. Okay, good. So if you're a really good artist or have very good 3-dimensional intuition, you could just draw a really accurate picture and see what you get. I'm not that. So I suggest that we try to write equations. Well, we have an equation for P. I suggest we try to write an equation for L. And then we set them equal and see what we can see. Okay, so how do we write an equation for L? I should first probably remind you, we haven't specified a line in this fashion yet, but remember from elementary geometry, which you took in high school, that in space, or in any dimensional space, 2 points specify exactly one line, right? But I know by elementary geometry that if I insist that I go through the point 530 and 622, that must specify a line. Now it's my job to interpret this in terms of vectors so I can write an equation for that line. So how should I proceed? Yeah.
Subtract the point 530 from 60.
Yeah, exactly. We'll find the displacement vector between these 2 points in space, right? By just subtracting one from the other. Good. So find a vector parallel to L. Find the displacement vector. Between the points. Okay, so that is to say, we'll let V be the vector given by the difference of the point 622 and the point 530 by vector arithmetic. Following? No. Of course, it doesn't actually matter what order I subtract them in, right? I'll still get a parallel vector to line up, but it's your suggestion. Okay, then we'll just write down parametric equations. Right, parametric equations. Okay, so I have a vector parallel. What else do I need for a parametric equation? The one. Yeah. A point. Yeah, and I'm given 2 points. It's immaterial which one I choose. I'm going to choose this one because it has a 0 in it. Make things drop out. Okay, so that is to say, what do I get from my parametric equations? X equals my x component of the point that is on the line minus t times the x component of the vector b. Y is equal to my y component, 3 plus t times the y component of the vector b. And z is equal to my z component, which is 0, t times 2. I don't like this. I have been writing t times a constant, but let's put the 2 out in front just to make it a standard looking coefficient. Yep. Okay. So where should we go from here? I kind of gave you a hint by choosing to write the parametric equations of this line out. Yeah. Yeah, exactly. I now have expressions for x, y, and z all in terms of a single parameter t. Therefore, if I plug in my expressions for x, y, and z into the plane, the equation for the plane, I'll have a single variable. and I can solve for t. Okay. So, plug expressions into equation for the plane P. So what do we get? We get 3 times our expression for x, 5 plus t, plus 2 times our expression for y, 3 minus t, minus z, our expression for z, 2t plus 6 equals 0. Okay, so if you use some algebra here, you'll find that t is equal to 27. Okay, so almost there. How do we now determine the point of intersection? Precisely. I plug in t to each of these expressions to find the value of x, y, and z, the point where the line intersects the plane. Okay, so implies what do we get here for? Okay, I'll write this. X evaluated at 27, y evaluated at 27, z evaluated at 27. Actually, do the arithmetic. Get 32, 24, 54. Yes. Sorry. Good. Thank you. Even when I compute 4 by, that's what we see. And the consequence of that is that you know, if you make the computational error, it's not going to what you're heading off. Okay, so is the point of intersection. Okay, so what happens in the other? Yes.
What would it look like if there's like no intersections? Like what would it be?
I was just about to ask you all the same question. Does anybody have an idea of what would happen if we were in either of the other 2 scenarios where L is parallel to the plane P? Either it lies on P or does not intersect. Yeah. Yeah. So if L lied on the plane P, then T would drop out of this equation and it would produce a true statement, like 0 equals 0 or 1 equals 1, something like that. If T does not intersect the plane P, T would also drop out and this would produce a false statement, like 1 equals 0 or something like that. Good question. Thank you. Good answer. Okay. Everybody comfortable with that? Okay, great. So I want to start now talking about the last topic of review. Remember, we talked about the dot product of vectors and how it's a efficient type of multiplication because you put 2 vectors in and you get a scalar out. We would like to have some notion of multiplication where we can multiply vectors and get a vector out. This in general is not possible, but in R3 in particular, we can make such a construction. called the cross product. Okay, so does anybody remember how to take the determinant of a 2 by 2 matrix? Yeah, I'm seeing some yeses, right? Let's remember. So call the determinant of a 2 by 2 matrix, say A, little a, A, B, C, D is defined by the following formula. I guess I should write this on the next board. Highlight its importance. So this is just something you have to memorize. There's very little I can say to justify this formula, but it's very nice. The determinant of A is equal to A times B minus B times C. That is to say, I multiply the diagonal and then I subtract the other diagonal multiple. Okay. So matrices in some ways behave a lot like vectors. The determinant is some kind of notion of the magnitude of a matrix. It can be negative, so it's not the same type of notion as magnitude, but it's some measure of size of a matrix, roughly. Okay, so why am I saying all this? This is because in order to compute the cross product, we're going to have to take the determinant of a 3 by 3 matrix. Taking determinants of arbitrary n by n matrices is a very time-consuming process and highly annoying. But 3 by 3 matrices, one step beyond a 2 by 2 is not so bad. And we'll only be doing it in this specific situation when we're working with cross products. So before we actually get to the technical details of computing a 3 by 3 determinant, we'll start with that tomorrow. Let me just tell you a little bit about the cross product in the next 2 minutes. Here's what the cross product does conceptually. You're given 2 vectors in R3. And what the cross product returns is a vector in R3, which is perpendicular to both of those vectors that you put in. Okay, so that is to say, if I have vector A and vector B, then the cross product will be a vector which is perpendicular to both of these vectors A and B. Okay, hopefully this drawing is somewhat clear. Right? These A and B are pointed out like this, and then I have my cross product like this. Remember what we said about determining the angle between 2 vectors in n-dimensional space, in this case in particular, 3-dimensional space. 2 vectors always span a plane as long as they're not parallel, right? So taking the cross product allows you to find a normal vector to that plane that they span. Okay, that's why we care about these things. It's very germane to all the discussion that we made today about how you can specify a plane by a normal vector and a point through. Okay, so that's our time. I'll see you all tomorrow. Have a good afternoon.